Hello everyone and welcome to lecture. In today's lecture we'll talk about solving systems of linear equations via the method of substitution and elimination, and then also look at a more refined procedure called row reduction. So the main idea here is that we can have, just like we can have linear equations in one dimension, we can have linear equations in many different number of variables, number of dimensions. Recall that in 1D, if I were to write down the equation mx is equal to b, this is an example of a linear equation in 1D, one dimension. Where m, x, and b are real numbers. Say m and b are known, right? So they're kind of fixed values, and x is unknown. So that the solution to this equation, as long as m is not equal to 0, is to just divide both sides by m. So x is equal to b over m, and that would be the solution for x in terms of b and m, the two known values in this equation. Now, if you were to take a linear algebra course, linear algebra is essentially generalizes this process to larger systems of equations, and it actually investigates more deeply mathematically how to do that and what the exact theorems are related to that. So for this lecture, we're going to kind of try to do a little bit of that, but just kind of do it basically. We'll show the main method of solving linear systems of equations. So a linear system of two variables looks very similar to this. However, there are two equations and two unknowns. So a general linear system of equations in 2D is a system of the form m11 times x plus m12 times y is equal to b1, and m21 times x plus m22 times y is equal to b2. For these values, mij and bk are real numbers, known real numbers. For all each possible combination of I, j, and k. So you can think about linear equations in 2D like this. So for example, a good example is the equation 2x minus y is equal to 1, and x plus y is equal to 5. This would be a good example of a system of two equations and two unknowns. Just to kind of be complete, I'll give an example of the 1D case as well. You could have the equation 3x is equal to pi, the solution of which is that x is equal to pi over 3. So we can also consider linear systems in more than just two variables. We can actually consider linear systems in any number of variables, and We're going to focus right now on systems of one variable, two variables, and three variables. But the idea is that this idea is very general. We can consider a system, say, of three unknown variables. So in the 2D example, x and y are the unknowns that we would have to solve for. A linear system of three variables, you'll have a number times x plus a number times y plus a number times z equal to some number b, b1 we'll call it. A number times x plus a number times y plus a number times z equal to some b2, and a number times x plus a number times y plus a number times z is equal to b3. So just to give you an example of a system like this, you could have, say, x plus y plus z is equal to 3, 2x plus y plus z is equal to 4, and then lastly x minus y plus 2z is equal to 5. And the problem, just like before, would be to solve for the unknowns, which are x, y, and z. So the idea is that there are two relatively basic methods that we'll first go over, called substitution and elimination. And really, you can use substitution and elimination for systems of three equations, systems of two equations, really systems of any number of linear equations. But really, they're only very convenient for systems of two equations and sometimes systems of three equations if the coefficients, the m values, work out nicely. But the point is that you can use this process of elimination or substitution to solve a system of any size of equations. But we'll see by the end of the lecture that there's a very nice, very, very straightforward algorithm called Gaussian elimination, that or row operations, that we can apply to any size linear system. So right off the bat, we want to get some basic definitions down. This is the definitions and classifications of what type of solutions we expect to find. And we really have three big terms that we want to define. The first term is a name for systems that have no solutions. So we say that a linear system of equations with no solutions is called inconsistent. So if you have a linear system and you can prove that it has no solutions, that system is an inconsistent system of linear equations. A linear system of equations with at least one solution, possibly more, is said to be consistent. Because we can find at least one solution to it. And one of the nice properties that we have is that a linear system of equations you can prove in linear algebra. You'd see this proven in a linear algebra course, that if a system of linear equations is consistent, then it has either one solution or infinitely many solutions. And the third point here is that any linear system with more than one solution and this is what I just said, has infinitely many solutions. In which case, we say that the system is called, it's dependent. And dependent on what, you could ask, it's dependent on the solution set. There's an infinite solution set for all of these solutions. They all lie on some set in some multidimensional space. So we'll go through and we'll introduce the substitution method right now, as well as the elimination method. So if we take our general linear system of two variables, and we write this down, and for ease of labeling, we'll call this equation 1 and this equation 2. The substitution method is as follows. If you go through and solve for one of the variables, so we'll solve equation 1 for x. well, this is going to be equal to m11 times x is equal to b1 minus m12 times y. So if I divide both sides by m11, x will be equal to b1 over m11 minus m12 over m11 times y. So this is what x is equal to in terms of b1, m11, m12, and y. So this is the first step, in some sense, of substitution. We solve for one of the variables. Now, we're not done yet, because x here is determined in terms of y, and y is still unknown. So we have to do something else, and that's step 2 of the substitution method. And essentially what that is to plug directly back into equation 2. So plug what we solved for x into equation 2. And doing this sort of isolates the variable y. So remember that equation 2 is m12 times x, which we solved for. It's b1 over m11 minus m12 over m11 times y plus m22 times y is equal to b2. That's equation 2 when we've substituted back in to equation 2 what we solved for for x in equation 1. Now we can rewrite this a little bit. If I distribute the m12, this is m12 over m11 times b minus m12 times oh, and I just realized that I made a small typo here. This should be m21 times x, because in general m21 is different than m12. So this should be m21 right here. This should be m21 right here as well. This is m12 times m21 over m11 times y plus m22 times y is equal to b2. And we can subtract this from both sides to sort of trying to isolate y. I can also factor out a y here. This is the same thing as y times m22 minus m12 times m21 over m11. And this is going to be equal to b2 minus m21 over m11 times b1. This is b1. Or if we simplify this a little bit, this becomes this. It's the same thing as y times, when I bring this subtraction to common denominator, it'll be m11 times m22 minus m12 times m21 over m11. When I bring this to common denominator, it becomes m11 times b2 minus m21 times b1, all over m11. The first thing that you want to notice is that I can multiply both sides of this equation by m11 to cancel out m11, and we are left with, when I solve for y, that y is equal to m11 times b2 minus m21 times b1 divided by this interesting expression right here, m11 times m22 minus m12 times m21. And this is the final solution for y, because it gives us y in terms of all of the known quantities. The general solution for any linear system. And we're almost done, but we also have to figure out what x is as well, because remember, we solve for x as well. So what we got for x is that x is equal to b1 minus m12 times y, all of this divided by m11, so we need to take this and also plug y back in for x to get our final value for x. So we have that x is equal to this, which is the same thing as b1 over m minus m12 over m11 times y, and y is m11 b2 minus m21 b1 divided by m11 times m22 minus m12 times m21. And when we bring this to common denominator, and after a little bit of algebra, what we'll end up seeing is that this is going to be exactly equal to the fraction negative m12 times b2 plus m22 times b1, all divided by m11 times m22 minus m12 times m21. There are a couple little steps for algebra there that I recommend going through and doing yourself to kind of practice your algebra techniques and your factoring and bringing the common denominator. It's a good exercise. But the main idea here is the following. We've solved our linear system in general for any values of m11, m22, m12, and m21, and b1, b2, as long as the denominator here is non-zero. So this the condition here for consistency is that this m11 times m22, because we're dividing by it, m11 times m22 minus m12 times m21 is non-zero. We'll see that this is actually a very important value called the determinant of the linear system. So the condition that this determinant is non-zero will give us consistency and will give us a solution to our linear system. So let's do this for our example problem and just kind of show exactly what how this works out for an example problem. It's a little bit shorter when you have actual numbers instead of the general solution. But I like presenting the general solution in general because it shows that we can do this for any coefficients as long as that determinant is non-zero. So for this system, we have equation 1 and equation 2. So step 1 is to solve equation 1 for x in terms of y. We do this by adding y to both sides of the expression and then dividing by 2 to get that x is equal to 1/2 plus y over 2 . And then for step 2, we substitute that into equation 2. So when we plug in for x into equation 2, x is equal to 1/2 plus y over 2. This is x plus y is equal to 5, which gives 1/2 plus y over 2 plus y is 3/2 times y is equal to 5, or 3/2 y is equal to 5 minus 1/2, or 9/2. And so y is equal to 9/2 times 2/3, or 9/3. Which I guess is probably more simply written as just 3. So y is equal to 3. And then we use that information, we plug back into equation 1. X is equal to 1/2 plus y over 2, which is 3 over 2, or 4 over 2, which is just equal to 2. So this linear system is consistent, and it has the solution of x equals 2, y equals 3. Now a nice way of sort of visualizing, which we can take with us into higher dimensions as well if we want to, in terms of visualizing solutions, is to visualize both of these linear equations in terms of what they represent geometrically. Equation 1, the equation 2x minus y equals 1, is the same thing as y is equal to 2x plus 1, or 2x minus 1. And equation 2 is the equation y is equal to 5 minus x. So equation 1 is a line of slope 2 so it has slope 2 and it has a y-intercept of 1 or negative 1. So it's the line going through these 2 points right here. This is equation 1. And the other equation is a line with y-intercept of 5. 1, 2, 3, 4, 5. And a slope of negative 1. This line right here. So this picture isn't exactly to scale, but what you see is that the intersection of these 2 lines is right here, and it's right at, it looks like x equals 2, y equals 3. So it's close enough, but it's not exactly to scale. So just keep that in mind. Just kind of drawing this freehand, but the idea here is that the solution we solve for exactly matches up with one point, and that point is the point x equals 2, y equals 3, which is the intersection of these 2 lines. So this is a kind of a nice picture. And this demonstrates the substitution method. Now you see, hopefully, that if you try and do this in general for a 3x3 system or a 4x4 system, a larger system of equations, it's going to quickly become very, very complicated, keeping track of all of the different substitutions that you'll have to do. Which is why it's definitely not the preferred method for even 3x3 systems. You don't want to think of them in terms of substitution. You can do it, but it takes a little while, and you got to keep track of all of the different substitutions. The same thing is said to be true about what's called the elimination method, which we'll talk about next. And in order to do that, I'm not going to derive the general solution, but you can do it in general, just like we did over here, to get this general solution, these general solution formulas. I'll just stick with this example because it's worthwhile to show how to do this. The main idea with the elimination method is to combine the 2 equations, or if it's more than 2 equations, the system of equations in ways that eliminate, but in clever ways, one of the variables. And for a system of more than two equations, it'll be one or more of the variables. So in our example, we're looking at the system of equations 2x minus y and x plus y. What you'll notice is that if I simply add these two equations together, so if I add equation 1 to equation 2, I'll get 2x plus x, and then negative y plus y is equal to 1 plus 5, and negative y plus y is 0, and 2x plus x is 3x, plus 0 is equal to 6, or x is equal to 6 over 3, which is equal to 2. So this is definitely quicker for this system than the substitution method was. Furthermore, we can go through and do the same thing in order to solve for y. If you take equation 1 and equation 2, this is, I guess, step 1 of the elimination method. It's choosing here to add these two equations together. When solving for y, it's a little bit more complicated, but it's not that much more complicated. What you'll notice is if I take and I add together equation 1 minus 2 times equation 2, or I subtract 2 times equation 2 from equation 1, then I'm going to get the following. I'll get 2x from equation 1 minus 2x from equation 2. I get minus y from equation 1 minus 2y from equation 2 on the left hand side, and that has to be equal to 1 minus 2 times 5. So 2x minus 2x is 0, minus y minus 2y is negative 3 times y, and negative 2 times 5 is negative 10, or negative 9. So it's 1 minus 2 times 5, which is 1 minus 10. So this is negative 9. So y is equal to negative 9 over negative 3, or positive 3. And there you have it. That's the elimination method for you. It's cleverly, looking at your system of equations and figuring out what you have to multiply by one equation and subtract or add to the other equation in order to cancel out one of the variables that you're solving for. And this again works anytime you're going to solve, and your system is a consistent system, so it has solutions. But what's not always easy is kind of generalizing it. If for a 2x2 system, it's relatively straightforward to do elimination. But even for a 3x3 system, it gets a little bit tricky sometimes. And never mind, in applications, typically you have systems that are huge, that are systems of maybe like 10,000 equations and 10,000 unknowns. You could have even larger systems. So we need to sort of find a method that will help us generalize and kind of fix this procedure for us, so we can do this for any number of any size system that we encounter in practice. And the main method here is what's called matrix notation is the notation we're going to be using, and the procedure is called Gaussian Elimination or row reduction. So in order to do this properly, we need to first introduce matrices and what's called matrix multiplication. A matrix is an m by n array of numbers. These are going to be complex numbers, or typically they're real numbers in a linear algebra course, but you can deal with complex numbers as well, and many linear algebra courses do. So for example, you could have a 2 by 3 matrix, and what these integers stand for, m and n are integers, and the first integer stands for the number of rows. So there's 2 rows in the array, and there's 3 columns in this array. So m is the number of rows, and n is the number of columns. So for example, a 2 by 3 matrix, you could have 4 pi e to the 1, 9, 10, 6. For example, a 3 by 3 matrix has 3 rows and 3 columns. So an example of this is maybe 1, 5, 9, 2, pi, 4. And then we need one more row in this. So we'll just take the row of values 6, 7, 2. This is an example of a 3 by 3 matrix. And a lot of times we can call a matrix capital A or capital B. We use capital letters to denote various matrices. So these are matrices, and we have a special class of matrices called vectors, and these are seen as matrices that have just one column in them. Typically we denote vectors as either one column or one row. So a column vector is like this, where there's say we'll do a 4 by 1 matrix, and for example it could be, say, x1, x2, x3, x4. So there's one column and there's 4 rows in this matrix, so we call this a column vector. Or you can think of a vector y as being what's called a row vector, and you'd take maybe a 1 by 3. So a good example of a row vector would be something of this form. Now we can define a very special type of multiplication between matrices, general matrices, that's called matrix multiplication. And essentially what this looks like for 2 by 2 matrices is the following. You have, say, a matrix. You have a matrix A, we'll call it, times a matrix B, where A is, say, A, B. We use A11, A12, A21, A22, multiplied by a matrix B, B11, B12, B21, B22. We say that the multiplication between the matrices A and B is computed in the following manner. For each individual entry in the resultant matrix, first off, the matrix multiplication of a 2 by 2 matrix with a 2 by 2 matrix will result always in another 2 by 2 matrix. And this is actually a general property that you can do this matrix multiplication, but the number of columns in the first matrix have to match up with the number of rows in the second matrix. So this first number here has to be the same as this number in order to make matrix multiplication make sense. But if you, in general, if you have an m by n matrix times an n by p matrix, the result that you're going to get is an m by p matrix. So in order to do this algorithm, the number of columns in the first matrix have to be equal to the number of rows in the second matrix. But the way that we compute this is we go through and we say, well, the ijth entry in the multiplication is just the multiplication of the ith row of A, the components of A, in the jth column of the components of B added together. So for instance, for the first, well, the 1, 1 entry in the matrix multiplication of A and B is going to be A11 times B11 plus A12 times B21. And so we'll call this multiplication, it's going to be a new matrix C. So we'll call it C11, C12, C21, C22. Now there is a definitive meaning behind why this multiplication is working the way that it does, and it comes directly from certain explanations in linear algebra that are a little bit more too advanced for this class. But essentially there's a meaning behind this definition of matrix multiplication. And we'll see an application shortly when we apply this to solving linear systems. So the idea is that this C12, or this entry of this new matrix, is going to be the first row in this matrix A multiplied by the entries in the second column of the matrix B, so that's C12, and those are going to be added together. So it'll be A11 times B12 plus A12 times B22. C21, this matrix multiplication, is going to be A21 times B11 plus A22 times B21, because it's the second row entries multiplied by the first column entries added together. And then lastly, it's going to be A11, right, A21 times B12 plus A22 times B22. So for two general matrices that are 2 by 2 matrices, this is how you multiply them together. You can also do the same thing. This algorithm works, like I said, if the number of rows in the second matrix is equal to the number of columns in the first matrix. So you can do this. It's called matrix vector multiplication. So say maybe something like A times X, where A is the vector, or the matrix A11, A12, A21, A22 times the vector X1, X2. So this is a 2 by 2 matrix being multiplied by a 2 by 1 matrix. And it's going to be the first row in this matrix times the first column in this matrix. And there's only going to be one entry because the matrix multiplication between a 2 by 2 and a 2 by 1 is going to be a 2 by 1, which is just another column vector. And the second entry will be A21 times X1 plus A22 times X2. And hopefully you're seeing in some sense where we're going with this, because we now actually have a means of writing down any size system of linear equations in a very nice, compact, simplified formula with this matrix vector multiplication. It's specifically for any 2 by 2 system that we talked about before. Even for 1 by 1 systems, you can think of them as, in 1D, the equation mx is equal to b. This is like a 1 by 1 matrix times a 1 by 1 matrix is equal to a 1 by 1 matrix. In 2D, it becomes a little bit more complicated, but it's still the same sort of idea. In 2D, if you write down a general linear equation, m11 times x plus m12 times y is equal to b1, m21 times x plus m22 times y is equal to b2. This is the same equation as the matrix equation, the matrix m11, m12, m21, m22 multiplied by the vector x, y is equal to the vector b1, b2. Or if I call this expression m, the matrix M, this expression the vector x, and this expression the vector b, this equation, the system of two equations and two unknowns, is what's called a matrix system. M times x is equal to b. So solving the system of equations amounts to solving, right, for the unknown vector x, which is just equal to x and y. And we can do this in general for any size system. It doesn't matter how big the system is, right? If we take our equation for a general system of 3 equations and 3 unknowns, the matrix multiplication algorithm is still the same. So for a system of 3 equations and 3 unknowns, x, y, and z, this system is the same thing as the matrix M11, M12, M13, M21, M22, M23, M31, M32, M33 times the vector of unknowns x, y, and z is equal to v1, v2, v3. Which, again, if we call this matrix M, if we call the unknowns vector x, and we call this vector b, and this equation is just the equation m times x is equal to b. Okay, it's a general way of dealing with systems. So if we can come up with a general procedure to follow, we can go through and actually solve linear systems that are very, very, very large with a given algorithm, if we can find an algorithm. And that exact algorithm is called row reduction or Gaussian elimination. So let's see how to do Gaussian elimination and what the basics of Gaussian elimination are for a given matrix. The main idea here is that we know that we can use substitution or elimination on these systems of equations, and we know that we can add any 2 linear equations together or multiply these linear equations by a given value, and that they'll stay the same as long as we multiply both sides by that value. So this elimination is based on that fact. It's based on the fact that we can do these operations. There are 3 main what are called row operations that we can do to a given matrix system, and will keep the system the same. So for example, right, if you look at our example system, our 2x2 system, this system of 2 equations right here, there are 3 main things that I can do with this system of equations that is not going to change this system of equations at all. And we actually use these 3 things when we're going through and we're doing the substitution method and the elimination method without even realizing it. So I can take and I can multiply this equation 1 right here by any value I want. I can multiply it by, just for example, you can multiply equation 1 by 3. In which case, if I do that, my system becomes 6x minus 3y is equal to 3, and then x plus y is equal to 5, which has the same solution as this system right here, because I'm not really changing anything. Right, so the first thing that I can do is multiply any equation, both sides, by a constant, and it remains unchanged. The other thing I can do is I can switch equation 1 with equation 2. I can say relabel. Say equation 1 is x plus y equals 5, and equation 2 is 2x minus y is equal to 1. So relabeling the equations. You relabel, it doesn't change the solution to the system of equations. It still has the same solution of that we solved for earlier. So you can relabel and still get the same solution for the equation names. The last thing we can do is we can subtract these two equations from one another, or add. So for example, I could add them together to get the equation. Let's say if I add them together, I get 3x plus 0 is equal to 1, or is equal to 6, 1 plus 5. And if I subtract them from one another, say I subtract equation 1 from equation 2, you'll get the equation x minus 2x, which is going to be negative x, and then y minus negative y, which will be plus 2y, and then lastly 5 minus 1 is equal to 4. So this system is looks different than this, but it has the exact same solution as the original system that we started with if you go through and solve this system. So these three changes are the basics and the basis for the steps in what's called the row reduction algorithm, or Gaussian elimination. And the idea, the main idea behind Gaussian elimination is the following. Well, it's because, or I should say it's based in some sense on the fact that this system is the same thing as the matrix system 2, negative 1, 1, 1 times x times y is equal to 1, 5. So we showed, and you can see by doing matrix vector multiplication, that when you do this matrix vector multiplication out, you'll just get, at the left hand side is going to give you 2x minus y for the first component, and it's going to give you x plus y for the second component. So this matrix vector multiplication is the same thing as the equation 2x minus y is equal to 1 and x plus y is equal to 5. So for a given system, what we do is we say that the augmented form of the system, or the augmented matrix that goes with the system, is the matrix M, along with the matrix on the left-hand side of the system, or the vector on the left-hand side of the system. So it's the matrix 2, negative 1, 1, 1, and you put a line, and then you put 1, 5. This is called the augmented matrix. For the system of equation 1 and equation 2. And what we do for the row reduction and the Gaussian elimination is the following. The whole goal is to put this augmented matrix into what's called reduced row echelon form. Reduced row echelon form is when you have ones in all of the leading, what are called leading columns, and in every column with a 1 you have zeros elsewhere in the column. So this is best shown with two main examples. We'll do the example that we already solved, that we know the solution of, and we'll do the example of that 3 by 3 matrix to kind of get a handle on how to do this. But the main three operations that we have are called row operations. And these row operations come directly from this discussion right here, that we can relabel the equations in any order we want, and the system will still be the same. We can multiply any equation by a constant, and then we can subtract or add any of the equations together to get a new system that has the same properties as the original system. So from these row operation, or from these operations, or these properties I should say, we have the following row operations. We can switch any rows in the augmented matrix and still get the same system. I should say it's another augmented matrix, because it will be different, but it represents the original system. So the main first row operation we have is from the relabeling property, which is that it doesn't matter what order you consider the system of equations in when you're trying to solve it. Property 2 is called row addition or subtraction. This means is that you can add any row of the augmented matrix to any other row and still get the same. It's a different augmented matrix, but it's still an augmented matrix that describes the original system. That has to do with this property right here, that we can, for a given linear system, you can take your linear equations and subtract or add them and still have a linear system that has the same solutions as the original linear system. And the last property and tool that we have for a row reduction algorithm is that we can do row multiplication. So what that means is that we can multiply any row of the augmented matrix by any constant value. I want to specify here, there should probably be non-zero value. And get another augmented matrix that is still equivalent in some sense to the original system. So the process of Gaussian elimination, and we'll stick again. This is general, and this by the way, these row operations and this idea holds not just for 2x2 systems, but for any size system. So we'll go through and do this for this specific 2x2 system, which has the augmented matrix from the example. Okay, this is the system. 2x minus y, x plus y, and that's equal to 1, 5. So this augmented matrix that we get is exactly this matrix right here. So typically we use a tilde to do row operations. From our multiplication row operation, this is the same thing as 1, negative 1/2, 1/2. If I divide by 2, or multiply by 1/2, we'll divide our 1 by 2. The next row operation we can do is subtract row 1 from row 2 from this matrix right here, which will give us still the same first row, but we get 1 minus 1 for this value. We get 1 minus negative 1/2 for this value, and 5 minus negative 1/2 for this value in the augmented matrix, which is the same thing as 1 negative 1/2 1/2 5 minus negative 1/2 is the same thing as 5 plus 1/2, or 11 halves. Oh, and sorry, this is not minus negative 1/2, it's just minus positive 1/2. I put a negative sign in there when I wasn't supposed to. It's 1 minus negative 1/2, which is this right here, and 5 minus positive 1/2, which is 9 halves. And that makes a little bit more sense based on what we got for our substitution before. So 9 halves. This is 0, and then 1 minus negative 1/2, or 1 minus negative 1/2 will be 5 plus 1/2, will be 1 plus 1/2, or 3 halves. And the next thing that we can do is we can multiply now row 2 by 2/3. Which will give us 0, 1, 1/2, and 2/3 times 9 halves is just 9/3. So this is the same thing as 1 negative 1/2 0, 1, 3, 1/2. And the last thing that I'm going to do here is, well, you're hopefully seeing what I'm seeing. We've actually just solved for y. If I do the matrix multiplication out here for our system, that this matrix times the vector xy is equal to this vector, you're going to get that x times 0, right, plus 1 times y is equal to 3, or y equals 3. So at this point, we've actually solved for y already. But if we keep going, we'll get the entire solution. This is sometimes called in echelon form, and it's similar to reduced row echelon form, but it's not fully in what's called reduced row echelon form, because you have a leading 1 here, it's called, but there's no zeros. There's a non-zero value above that leading 1. So this matrix is not in reduced row echelon form just yet. But we can put it into reduced row echelon form, and I'll combine 2 steps. I'm going to multiply row 2 by 1/2, and then subtract that from row 1. So 0 times 1/2 is 0, and when I subtract that from 1, I'm left with 0. I'm left with 1, sorry. 1 minus 0 is 0. Multiply this value by 1/2. Oh, and I don't want to subtract it either. I was moving a little bit too fast there. I apologize for that. When I multiply it by 1/2 and add it to row 1. I multiply 0 times 1/2 and I add it to 1, I get 1 plus 0, which is just 1. Multiply 1 by 1/2 and add it to negative 1/2, I get 0. And lastly, I multiply 3 by 1/2 and add it to 1/2, I get 3/2 plus 1/2, which is the same thing as 1, 0, 0, 1, and this is 4/2. This is 3, which is the same thing as 1, 0, 0, 1, 2, 3. And this tells me directly that the solution to this system of equations is 2 and 3. Because what this is saying is that our original system is equivalent to the system 1, 0, 0, 1 matrix multiplied with x, y is equal to 2, 3. And this matrix multiplication done out is just x times 1 plus 0. This is going to be 0 times x plus 1 times y, which is y, is equal to 2, 3. So this is Gaussian elimination done on this 2x2 system. And it's a very, very powerful method indeed, because this algorithm applies to solving not just 2x2 systems, but really any number of systems of linear equations. So let's end the lecture by doing the last example that I started with at the very beginning of class. So we'll look at this system of equations, and we'll look at and try and figure out how to do this and do row reduction on this system of equations. The first step is always to put it into what's called Echelon form, which is zeros on the lower diagonal of this matrix. And I guess even before that, our step 0 is probably to rewrite the augmented form of the system. This system is equivalent to the system 1, 1, 1, 2, 1, 2, or 2, 1, 1, 1, negative 1, 2, times the unknown vector x, y, and z is equal to 3, 4, 5. So the augmented form of the system is going to be 1, 1, 1, 2, 1, 1, 1, negative 1, 2. We put a line, 3, 4, 5. So what we'll do first to simplify things is we'll keep this the way it is, but I'm going to take and do 2 times the first row, and I'm going to subtract that from the second row. So I want to get rid of this 2 right here, make it a 0. This is 1, 1, 1, 3. 2 times 1 is 2. 2 minus 2 is 0. 2 times 1 is 2. 1 minus 2 is negative 1. 2 times 1 is 2. 1 minus 2 is negative 1. 2 times 3 is 6. 4 minus 6 is negative 2. And then for the next step as well, you can very quickly do 2 more row reduction steps. I'll just do R3 minus R1. We do R3 minus R1, then 1 minus 1 is going to be 0. Everything else stays the same. 1, 1, 1, 3. 1 minus 1 is going to be 0. Negative 1 minus 1 is going to be negative 2. 2 minus 1 is going to be 1. And 5 minus 3 is going to be 2. Then this row stays the same as well. So it's 0, negative 1, negative 1, negative 2. So I'm going to multiply the second row by negative 1. To get 0, 1, 1, 2. We give this a 0, negative 2, negative 1, or negative 2, positive 1, 2. And to get rid of this term right here, I'll just do 2 times row 2, or row 2, plus row 3. Which will give me 0, because 2 times 0 plus 0 is 0. 2 times 1 plus negative 2 is 0. 2 times 1 plus 1 is 3. Oh, and this last one is not going to be 2. This is going to be 2 times 2 is 4, plus 2 is 6. So the last thing that we can do for the first part of Gaussian elimination, so we're doing R1 minus R2, which will be 1 minus 0, which is 1, 1 minus 1, which is 0, 1 minus 1, which is 0, and 3 minus 2, which is 1. And then we'll also do R2 minus R3 as well. That'll be 0 minus 0, 1 minus 0, which is 1, and then 1 minus 1, which is equal to 0. That becomes 2 minus 2, which is 0. And then lastly, this is going to stay the same. Row 3 will stay the same. So this essentially is it. This is what's called a reduced row echelon form. And our solution is given directly as follows. It's that x is equal to 1, y is equal to 0, and z is equal to 2. This is the exact solution to the original system that we started with, this system of 3 equations. So you can see that it's much more convenient to use this row reduction form and to use this row reduction way algorithm for computing the solution to this linear system. And it is definitely more efficient when you deal with larger and larger and larger systems. That will conclude today's lecture. Thank you very much for listening, and I hope you learned something and had a great day.